Indicated horsepower. The indicated horsepower produced by an engine is the horsepower calculated from the indicated mean effective pressure and the other factors which affect the power output of an engine. Indicated horsepower is the power developed in the combustion chambers without reference to friction losses within the engine. This horsepower is calculated as a function of the actual cylinder pressure recorded during engine operation. To facilitate the indicated horsepower calculations, a mechanical indicating device, such as is attached to the engine cylinder, captures the actual pressure existing in the cylinder during the complete operating cycle. This pressure variation can be represented by the kind of graph shown in Figure 1-39. Notice that the cylinder pressure rises on the compression stroke, reaches a peak after top center, and decreases as the piston moves down on the power stroke. Since the cylinder pressure varies during the operating cycle, an average pressure, line AB, is computed. This average pressure, if applied steadily during the time of the power stroke, would do the same amount of work as the varying pressure during the same period. This average pressure is known as indicated mean effective pressure and is included in the indicated horsepower calculation with other engine specifications. If the characteristics and the indicated mean effective pressure of an engine are known, it is possible to calculate the indicated horsepower rating. The indicated horsepower for a 4-stroke cycle engine can be calculated from the following formula, in which the letter symbols in the numerator are arranged to spell the word Planck. To assist in memorizing the formula, indicated horsepower equals Planck 33,000, where P equals indicated mean effective pressure, in psi L equals length of the stroke, in feet or in fractions of a foot equals area of the piston head or cross-sectional area of the cylinder, in square inches, N equals number of power strokes per minute, RPM 2K equals number of cylinders. In the formula above, the area of the piston multiplied by the indicated mean effective pressure gives the force acting on the piston in pounds. This force multiplied by the length of the compression power exhaust intake, peak pressure, pressure in cylinder, P, A, B, indicated mean effective pressure, IMP, spark, DC, E, I, bottom center top center BCTC BC. Figure 1-39. Compression ratio 1-31. Stroke in feet gives the work performed in one power stroke, which, multiplied by the number of power strokes per minute, gives the number of foot-pounds per minute of work produced by one cylinder. Multiplying this result by the number of cylinders in the engine gives the amount of work performed, in foot-pounds, by the engine. Since HP is defined as work done at the rate of 33,000 feet-pounds per minute, the total number of foot-pounds of work performed by the engine is divided by 33,000 to find the indicated horsepower. Example. Given, indicated mean effective pressure, P, equals 1.65 pounds/into stroke, L, equals 6 in or 0.5 feet bore equals 0.5 in RPM equals 3,000 of cylinders, K, equals 12. Indicated HP equals Planck 33,000 feet-pounds/min. Find indicated HP is found by using the equation A equals 1/4 pi d2. A equals 1/4 times 3.1416 times 5.5 in times 5.5 in equals 23.76 into N is found by multiplying the RPM by 1/2. N equals 1/2 times 3,000 equals 1,500 RPM. Now, substituting in the formula, indicated HP equals 1.65 pounds/into times 0.5 in times 23.76 in 2 times 1,500 RPM times 12 33,000 feet-pounds/min. Indicated HP equals 1,069.20. Brake horsepower. The indicated horsepower calculation discussed in the preceding paragraph is the theoretical power of a frictionless engine. The total horsepower lost in overcoming friction must be subtracted from the indicated horsepower to arrive at the actual horsepower delivered to the propeller. The power delivered to the propeller for useful work is known as brake horsepower, BHP. The difference between indicated and brake horsepower is known as friction horsepower, which is the horsepower required to overcome mechanical losses, such as the pumping action of the pistons, the friction of the pistons, and the friction of all other moving parts. The measurement of an engine's BHP involves the measurement of a quantity known as torque or twisting moment. Torque is the product of a force, and the distance of the force from the axis about which it acts. Or, torque equals force times distance, at right angles to the force. Torque is a measure of load, and is properly expressed in pound-inches, pounds in, or pound-feet, pounds-foot. Torque should not be confused with work, which is expressed in inch-pounds, in pounds, or foot-pounds, foot-pounds. There are numerous devices for measuring torque, such as a dynamometer or a torque meter. One very simple type of device that can be used to demonstrate torque calculations is the Prony brake. Figure 1-40. All of these torque measuring devices are usable to calculate power output of an engine on a test stand. It consists essentially of a hinged collar, or brake, which can be clamped to a drum spline to the propeller shaft. The collar and drum form a friction brake, which can be adjusted by a wheel. An arm of unknown length is rigidly attached to, or is a part of the hinged collar, and terminates at a point that rests on a set of scales. As the propeller shaft rotates, it tends to carry the hinged collar of the brake with it, and is prevented from doing so only by the arm that rests on the scale. The scale indicates the force necessary to arrest the motion of the arm. If the resulting force registered on the scale is multiplied by the length of the arm, the resulting product is the torque exerted by the rotating shaft. For example, if the scale registers 200 pounds, and the length of the arm is 3.18 feet, the torque exerted by the shaft is 200 pounds times 3.18 feet equals 636 pounds-foot. Once the torque is known, the work done per revolution of the propeller shaft can be computed without difficulty by the equation, work per revolution equals 2 pi times torque. If work per revolution is multiplied by the RPM, the result is work per minute, or power. If the work is expressed in foot-pounds per minute, this quantity is divided by 33,000. The result is the brake horsepower of the shaft. Power equals work per revolution times RPM, and bhp equals work per revolution times RPM 33,000. 2 pi r times force on the scales, pounds times length of arm, foot times RPM, 33,000. 1-32. Scale 200 pounds. 0. Friction adjusting wheel, 300,100. Collar, arm hinge, 200. Drum, propeller shaft, length of arm 3.18 feet. Figure 1-40. Typical Prony brake. Example. Given, force on scales equals 200 pounds, length of arm equals 3.18 feet, RPM equals 3,000. Pi equals 3.1416. Find bhp substituting in equation. bhp equals 6.2832 times 200 times 3.18 times 3,000. 33,000. Equals 363.2. Equals 363. As long as the friction between the brake collar and propeller shaft drum is great enough to impose an appreciable load on the engine, but is not great enough to stop the engine, it is not necessary to know the amount of friction between the collar and drum to compute the bhp. If there were no load imposed, there would be no torque to measure, and the engine would run away. If the imposed load is so great that the engine stalls, there may be considerable torque to measure, but there is no RPM. In either case, it is impossible to measure the bhp of the engine. However, if a reasonable amount of friction exists between the brake drum and the collar, and the load is then increased, the tendency of the propeller shaft to carry the collar and arm about with it becomes greater, thus imposing a greater force upon the scales. As long as the torque increase is proportional to the RPM decrease, the horsepower delivered at the shaft remains unchanged. This can be seen from the equation in which 2 pi r and 33,000 are constants, and torque and RPM are variables. If the change in RPM is inversely proportional to the change in torque, their product remains unchanged, and bhp remains unchanged. This is important. It shows that horsepower is the function of both torque and RPM, and can be changed by changing either torque, RPM, or both. Friction horsepower. Friction horsepower is the indicated horsepower minus brake horsepower. It is the horsepower used by an engine in overcoming the friction of moving parts, drawing in fuel, expelling exhaust, driving oil, and fuel pumps, and other engine accessories. On modern aircraft engines, this power loss through friction may be as high as 10 to 15% of the indicated horsepower. Friction and brake mean effective pressures. The indicated mean effective pressure, IMP, discussed previously, is the average pressure produced in the combustion chamber during the operating cycle, and is an expression of the theoretical frictionless power known as indicated horsepower. In addition to completely disregarding power loss to friction. 1-33. FMEP, BMEP, IMP. Figure 1-41. Power and pressure. Indicated horsepower gives no indication of how much actual power is delivered to the propeller shaft for doing useful work. However, it is related to actual pressures that occur in the cylinder, and can be used as a measure of these pressures to compute the friction loss and net power output. The indicated horsepower of a cylinder may be thought of as two separate powers, each producing a different effect. The first power overcomes internal friction, and the horsepower thus consumed is known as friction horsepower. The second power, known as brake horsepower, produces useful work at the propeller. That portion of IMP that produces brake horsepower is called brake mean effective pressure, BMEP. The remaining pressure used to overcome internal friction is called friction mean effective pressure, FMEP. Figure 1-41, IMP is a useful expression of total cylinder power output, but is not a real physical quantity. Likewise, FMEP and BMEP are theoretical but useful expressions of friction losses and net power output. Although BMEP and FMEP have no real existence in the cylinder, they provide a convenient means of representing pressure limits or rating engine performance throughout its entire operating range. There is an operating relationship between IMP, BMEP, and FMEP. One of the basic limitations placed on engine operation is the pressure developed in the cylinder during combustion. In the discussion of compression ratios and indicated mean effective pressure, it was found that, within limits, increased pressure resulted in increased power. It was also noted that if the cylinder pressure were not controlled within closed limits, it would impose dangerous internal loads that might result in engine failure. Therefore, it is important to have a means of determining these cylinder pressures as a protective measure, and for efficient application of power. If the BHP is known, the BMEP can be computed by means of the following equation. BMEP equals BHP times 33,000 length given, BHP equals 1,000. Stroke equals 6 in bore equals 5.5 in RPM equals 3,000. Number of cycles equals 12. Find BMEP. Find length of stroke, in foot. L equals 6 in equals 0.5 feet. Find area of cylinder bore. A equals 1/4 pyro 2. A equals 1/4 times 3.1416 times 5.5 in times 5.5 in A equals 23.76 in 2. Power stroke. Actual pressure. IMP. TCBC. Friction. FHP. Accessories BHP. Impeller. 1-34. Find number of power strokes per min. N equals 1/2 times RPM. N equals 1/2 times 3000 RPM. N equals 1500 then. Substituting in the equation, BMEP equals 1000 BHP times 33,000 feet-pounds slash min 0.5 feet times 23.76 and 2 times 1500 strokes slash min times 12 equals 154.32 pounds slash in 2. Thrust horsepower. Thrust horsepower can be considered the result of the engine and the propeller working together. If a propeller could be designed to be 100% efficient, the thrust and the BPH would be the same. However, the efficiency of the propeller varies with the engine speed, attitude, altitude, temperature, and airspeed. Thus, the ratio of the thrust horsepower and the BHP delivered to the propeller shaft will never be equal. For example, if an engine develops 1000 BHP and it is used with a propeller having 85% efficiency, the thrust horsepower of that engine propeller combination is 85% of 1000, or 850 thrust HP. Of the 4 types of horsepower discussed, it is the thrust horsepower that determines the performance of the engine propeller combination. Efficiencies. Thermal efficiency. Any study of engines and power involves consideration of heat as the source of power. The heat produced by the burning of gasoline in the cylinders causes a rapid expansion of the gases in the cylinder. And this, in turn, moves the pistons and creates mechanical energy. It has long been known that mechanical work can be converted into heat, and that a given amount of heat contains the energy equivalent of a certain amount of mechanical work. Heat and work are theoretically interchangeable and bear a fixed relation to each other. Heat can therefore be measured in work units, for example, foot-pounds, as well as in heat units. The British thermal unit, BTU, of heat is the quantity of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. It is equivalent to 778 feet-pounds of mechanical work. A pound of petroleum fuel, when burned with enough air to consume it completely, gives up about 20,000 BTU, the equivalent of 15,560,000 feet-pounds of mechanical work. These quantities express the heat energy of the fuel in heat and work units, respectively. The ratio of useful work done by an engine to the heat energy of the fuel it uses, expressed in work or heat units, is called the thermal efficiency of the engine. If 2 similar engines use equal amounts of fuel, the engine that converts into work the greater part of the energy in the fuel, higher thermal efficiency, delivers the greater amount of power. Furthermore, The engine that has the higher thermal efficiency has less waste heat to dispose of to the valves, cylinders, pistons, and cooling system of the engine. A high thermal efficiency also means low specific fuel consumption, and, therefore, less fuel for a flight of a given distance at a given power. Thus, the practical importance of a high thermal efficiency is threefold, and it constitutes one of the most desirable features in the performance of an aircraft engine. Of the total heat produced, 25 to 30% is utilized for power output, 15 to 20% is lost in cooling, heat radiated from cylinder head fins, 5 to 10% is lost in overcoming friction of moving parts, and 40 to 45% is lost through the exhaust. Anything that increases the heat content going into mechanical work on the piston, which reduces the friction and pumping losses, or which reduces the quantity of unburned fuel or the heat lost to the engine parts, increases the thermal efficiency. The portion of the total heat of combustion that is turned into mechanical work depends to a great extent upon the compression ratio. The compression ratio is the ratio of the piston displacement plus combustion chamber space to the combustion chamber space, as mentioned earlier. Other things being equal, the higher the compression ratio is, the larger is the proportion of the heat energy of combustion turned into useful work at the crankshaft. On the other hand, increasing the compression ratio increases the cylinder head temperature. This is a limiting factor, because the extremely high temperature created by high compression ratios causes the material in the cylinder to deteriorate rapidly, and the fuel to detonate instead of burning at a controlled rate. The thermal efficiency of an engine may be based on either bhp, or indicated horsepower, and is represented by the formula. Indicated thermal efficiency equals A times 33,000 weight of fuel burned / minutes times heat value times 778. The formula for brake thermal efficiency is the same as shown above, except the value for bhp is inserted instead of the value for A. Example: an engine delivers 85 bhp for a period of 1 hour, and during that time consumes 50 pounds of fuel. Assuming the fuel has a heat content of 18,800 BTU per pound, find the thermal efficiency of the engine. 85 times 33,000 equals 2,805,000. 0.833 times 18,800 BTU times 778, 12,184,569. 1-35. Brake thermal efficiency equals 0.23 or 23%. Reciprocating engines are only about 34% thermally efficient. That is, they transform only about 34% of the total heat potential of the burning fuel into mechanical energy. The remainder of the heat is lost through the exhaust gases, the cooling system, and the friction within the engine. Thermal distribution in the reciprocating engine is illustrated in Figure 1-42. Mechanical efficiency. Mechanical efficiency is the ratio that shows how much of the power developed by the expanding gases in the cylinder is actually delivered to the output shaft. It is a comparison between the bhp and the A. It can be expressed by the formula: mechanical efficiency equals bhp A. Brake horsepower is the useful power delivered to the propeller shaft. Indicated horsepower is the total HP developed in the cylinders. The difference between the two is friction horsepower, FHP, the power lost in overcoming friction. The factor that has the greatest effect on mechanical efficiency is the friction within the engine itself. The friction between moving parts in an engine remains practically constant throughout an engine speed range. Therefore, the mechanical efficiency of an engine is highest when the engine is running at the RPM at which maximum bhp is developed. Mechanical efficiency of the average aircraft reciprocating engine approaches 90%. Volumetric efficiency. Volumetric efficiency is a ratio expressed in terms of percentages. It is a comparison of the volume of fuel/air charge, corrected for temperature and pressure, inducted into the cylinders to the total piston displacement of the engine. Various factors cause departure from a 100% volumetric efficiency. The pistons of a naturally aspirated engine displace the same volume each time they travel from top center to bottom center of the cylinders. The amount of charge that fills this volume on the intake stroke depends on the existing pressure and temperature of the surrounding atmosphere. Therefore, to find the volumetric efficiency of an engine, standards for atmospheric pressure and temperature had to be established. The U.S. standard atmosphere was established in 1958 and provides the necessary pressure and temperature values to calculate volumetric efficiency. The standard sea level temperature is 59 degrees Fahrenheit, or 15 degrees Celsius. At this temperature, the pressure of 1 atmosphere is 14.69 pounds/2. And this pressure supports a column of mercury, Hg, 29.92 inches high, or 29.92 Hg. These standard sea level conditions determine a standard density. And if the engine draws in a volume of charge of this density exactly equal to its piston displacement, it is said to be operating at 100% volumetric efficiency. An engine drawing in less volume than this has a volumetric efficiency lower than 100%. An engine equipped with true supercharging, boost above 30.00 Hg, may have a volumetric efficiency greater than 100%. The equation for volumetric efficiency is volumetric volume of charge corrected for efficiency equals temperature and pressure, piston displacement. Many factors decrease volumetric efficiency, including part throttle operation, long intake pipes of small diameter, sharp bends in the induction system, carburetor air temperature too high, cylinder head temperature too high, incomplete scavenging, heat released by combustion. 40-45% is carried out with exhaust. 15-20% is removed by fins. 25-30% is converted into useful power. 5-10% is removed by the oil. Figure 1-42. Thermal distribution in an engine. 1-36. Improper valve timing. Propulsive efficiency. A propeller is used with an engine to provide thrust. The engine supplies bhp through a rotating shaft, and the propeller absorbs the bhp and converts it into thrust hp. In this conversion, some power is wasted, since the efficiency of any machine is the ratio of useful power output to the power input. Propulsive efficiency, in this case, propeller efficiency, is the ratio of thrust hp to bhp. On the average, thrust hp constitutes approximately 80% of the bhp. The other 20% is lost in friction and slippage. Controlling the blade angle of the propeller is the best method of obtaining maximum propulsive efficiency for all conditions encountered in flight. During takeoff, when the aircraft is moving at low speeds, and when maximum power and thrust are required, a low propeller blade angle gives maximum thrust. For high-speed flying or diving, the blade angle is increased to obtain maximum thrust and efficiency. The constant speed propeller is used to give required thrust at maximum efficiency for all flight conditions. Gas turbine engines, types, and construction. In a reciprocating engine, the functions of intake, compression, combustion, and exhaust all take place in the same combustion chamber. Consequently, each must have exclusive occupancy of the chamber during its respective part of the combustion cycle. A significant feature of the gas turbine engine is that separate sections are devoted to each function, and all functions are performed simultaneously without interruption. A typical gas turbine engine consists of 1. An air inlet. 2. Compressor section. 3. Combustion section. 4. Turbine section. 5. Exhaust section. 6. Accessory section. And 7. The systems necessary for starting, lubrication, fuel supply, and auxiliary purposes, such as anti-icing, cooling, and pressurization. The major components of all gas turbine engines are basically the same. However, the nomenclature of the component parts of various engines currently in use varies slightly due to the difference in each manufacturer's terminology. These differences are reflected in the applicable maintenance manuals. One of the greatest single factors influencing the construction features of any gas turbine engine is the type of compressor or compressors for which the engine is designed. 4 types of gas turbine engines are used to propel and power aircraft. They are the turbofan, turboprop, turboshaft, and turbojet. The term turbojet was used to describe any gas turbine engine used in aircraft. As gas turbine technology evolved, these other engine types were developed to take the place of the pure turbojet engine. The turbojet engine has problems with noise and fuel consumption in the speed range that airliners fly. 8 Mach. Due to these problems, use of pure turbojet engines is very limited. So, almost all airliner-type aircraft use a turbofan engine. It was developed to turn a large fan or set of fans at the front of the engine, and produces about 80% of the thrust from the engine. This engine was quieter, and has better fuel consumption in this speed range. Turbofan engines have more than one shaft in the engine. Many are 2-shaft engines. This means that there are 2 sets of compressors and turbines that drive them. These 2-shafted engines use 2 spools. A spool is a compressor and a shaft, and turbines that driven that compressor. In a 2-spool engine, there is a high-pressure spool and a low-pressure spool. The low-pressure spool generally contains the fans and the turbine stages it takes to drive them. The high-pressure spool is the high-pressure compressor, shaft, and turbines. This spool makes up the core of the engine, and this is where the combustion section is located. Turbofan engines can be low bypass or high bypass. The amount of air that is bypassed around the core of the engine determines the bypass ratio. As can be seen in Figure 1-43, the air generally driven by the fan does not pass through the internal working core of the engine. The amount of airflow in pounds/seconds from the fan bypass to the core flow of the engine is the bypass ratio. Bypass ratio equals 100 pounds divided by seconds flow fan equals 5. 1 bypass ratio 20 pounds/seconds flow core. Some low bypass turbofan engines are used in speed ranges above 0.8 Mach military aircraft. These engines use augmenters or afterburners to increase thrust. By adding more fuel nozzles and a flame holder in the exhaust system, extra fuel can be sprayed and burned, which can give large increases in thrust for short amounts of time. The turboprop engine is a gas turbine engine that turns a propeller through a speed reduction gearbox. This type of engine is most efficient in the 300 to 400 miles per hour speed range and can use shorter runways than other aircraft. Approximately 80 to 85% of the energy developed by the gas turbine engine is used to drive the propeller. The rest of the available energy exits the exhaust as thrust. By adding the horsepower 1-37 developed by the engine shaft and the horsepower in the exiting thrust, the answer is equivalent shaft horsepower. With regard to aircraft, the Turboshaft Engine is a gas turbine engine made to transfer horsepower to a shaft that turns a helicopter transmission, or is an onboard auxiliary power unit, APU. An APU is used on turbine-powered aircraft to provide electrical power and bleed air on the ground, and a backup generator in flight. Turboshaft engines can come in many different styles, shapes, and horsepower ranges. Air entrance. The air entrance is designed to conduct incoming air to the compressor with a minimum energy loss resulting from drag or ram pressure loss. That is, the flow of air into the compressor should be free of turbulence to achieve maximum operating efficiency. Proper inlet design contributes materially to aircraft performance by increasing the ratio of compressor discharge pressure to duct inlet pressure. This is also referred to as the compressor pressure ratio. This ratio is the outlet pressure divided by the inlet pressure. The amount of air passing through the engine is dependent upon three factors. 1. The compressor speed, RPM. 2. The forward speed of the aircraft. 3. The density of the ambient, surrounding, air. Turbine inlet type is dictated by the type of gas turbine engine. A high bypass turbofan engine inlet is completely different from a turboprop or turboshaft inlet. Large gas turbine-powered aircraft almost always have a turbofan engine. The inlet on this type of engine is bolted to the front, a flange, of the engine. These engines are mounted on the wings, or nacelles, on the aft fuselage, and a few are in the vertical fin. A typical turbofan inlet can be seen in Figure 1-44. Since on most modern turbofan engines the huge fan is the first part of the aircraft the incoming air comes into contact with, icing protection must be provided. This prevents chunks of ice from forming on the leading edge of the inlet, breaking loose, and damaging the fan. Warm air is bled from the engine's compressor and is ducted through the inlet to prevent ice from forming. If inlet guide vanes are used to straighten the airflow, then they also have anti-icing air flowing through them. The inlet also contains some sound-reducing materials that absorb the fan noise and make the engine quieter. Turboprops and turboshafts can use an inlet screen to help filter out ice or debris from entering the engine. A deflector vane and a heated inlet lip are used to prevent ice from forming and allowing large chunks to enter the engine. On military aircraft, the divided entrance permits the use of very short ducts with a resultant small pressure drop through skin friction. Military aircraft can fly at speeds above Mach 1, but the airflow through the engine must always stay below Mach 1. Supersonic airflow in the engine would destroy the engine. By using convergent and divergent shaped ducts, the airflow is controlled and dropped to subsonic speeds before entering the engine. Supersonic inlets are used to slow the incoming engine air to less than Mach 1 before it enters the engine. Accessory Section. The accessory section of the gas turbine engine has various functions. The primary function is to provide space for Figure 1-43. Turbofan engine with separate nozzles, fan, and core. 1-38. Figure 1-44. Typical turbofan inlet. The mounting of accessories necessary for operation and control of the engine. Generally, it also includes accessories concerned with the aircraft, such as electric generators and hydraulic pumps. Secondary functions include acting as an oil reservoir and / or oil sump, and housing the accessory drive gears and reduction gears. The arrangement and driving of accessories has always been a major problem on gas turbine engines. Driven accessories on turbofans are usually mounted on the accessory gearbox, which is on the bottom of the engine. The location of the accessory gearbox varies somewhat, but most turboprops and turboshafts have the accessory cases mounted to the back section of the engine. The components of the accessory section of all gas turbine engines have essentially the same purpose, even though they often differ quite extensively in construction details and nomenclature. The basic elements of the accessory section are 1. The accessory case, which has machined mounting pads for the engine-driven accessories, and 2. The gear train, which is housed within the accessory case. The accessory case may be designed to act as an oil reservoir. If an oil tank is utilized, a sump is usually provided below the front bearing support for the drainage and scavenging of oil used to lubricate bearings and drive gears. The accessory case is also provided with adequate tubing or cord passages for spraying lubricating oil on the gear train and supporting bearings. The gear train is driven by the engine high-pressure compressor through an accessory drive shaft, tower shaft, gear coupling, which splins with the gearbox gear, and the high-pressure compressor. The reduction gearing within the case provides suitable drive speeds for each engine accessory or component. Because the rotor operating RPM is so high, the accessory reduction gear ratios are relatively high. The accessory drives are supported by ball bearings assembled in the mounting pad bores of the accessory case. Figure 1-45. Compressor Section. The compressor section of the gas turbine engine has many functions. Its primary function is to supply air in sufficient quantity to satisfy the requirements of the combustion burners. Specifically, to fulfill its purpose, the compressor must increase the pressure of the mass of air received from the air inlet duct, and then discharge it to the burners in the quantity and at the pressures required. A secondary function of the compressor is to supply bleed air for various purposes in the engine and aircraft. The bleed air is taken from any of the various pressure stages of the compressor. The exact location of the bleed ports is, of course, dependent on the pressure or temperature required for a particular job. The ports are small openings in the compressor case adjacent to the particular stage from which the air is to be bled. Thus, varying degrees of pressure are available simply by tapping into the appropriate stage. Air is often bled from the final or highest pressure stage since, at this point, pressure and air temperature are at a maximum. At times it may be necessary to cool this high-pressure air. If it is used for cabin pressurization or other purposes to which excess heat would be uncomfortable or detrimental, the air is sent through an air conditioning unit before it enters the cabin. Figure 1-45. Typical turboprop accessory case. 1-39. A B. Impeller diffuser compressor manifold. Air outlet elbow with turning vanes for reducing air pressure losses. Figure 1-46. A. Components of a centrifugal flow compressor. B. Air outlet elbow with turning vanes for reducing air pressure losses. Bleed air is utilized in a wide variety of ways. Some of the current applications of bleed air are 1. Cabin pressurization, heating, and cooling. 2. De-icing and anti-icing equipment. 3. Pneumatic starting of engines. And 4. Auxiliary drive units, ADU. Compressor types. The two principal types of compressors currently being used in gas turbine aircraft engines are centrifugal flow and axial flow. The centrifugal flow compressor achieves its purpose by picking up the entering air and accelerating it outwardly by centrifugal action. The axial flow compressor compresses air while the air continues in its original direction of flow, thus avoiding the energy loss caused by turns. The components of each of these two types of compressor have their individual functions in the compression of air for the combustion section. A stage in a compressor is considered to be a rise in pressure. Centrifugal flow compressors. The centrifugal flow compressor consists of an impeller, rotor, a diffuser, stator, and a compressor manifold. Figure 1-46. Centrifugal compressors have a high pressure rise per stage that can be around 8.1. Generally, centrifugal compressors are limited to 2 stages due to efficiency concerns. The two main functional elements are the impeller and the diffuser. Although the diffuser is a separate unit and is placed inside and bolted to the manifold, the entire assembly, diffuser, and manifold, is often referred to as the diffuser. For clarification during compressor familiarization, the units are treated individually. The impeller is usually made from forged aluminum alloy, heat-treated, machined, and smoothed for minimum flow restriction and turbulence. In most types, the impeller is fabricated from a single forging. This type impeller is shown in Figure 1-46. The impeller, whose function is to pick up and accelerate the air outwardly to the diffuser, may be either of two types, single entry or double entry. The principal differences between the two types of impellers are size and ducting arrangement. The double entry type has a smaller diameter, but is usually operated at a higher rotational speed to assure sufficient airflow. The single entry impeller, shown in figure 1-47, permits convenient ducting directly to the impeller eye, inducer vanes, as opposed to the more complicated ducting necessary to reach the rear side of the double entry type. Although slightly more efficient in receiving air, the single entry impeller must be large in diameter to deliver the same quantity of air as the double entry type. This, of course, increases the overall diameter of the engine. Figure 1-47. Single entry impeller. 1-40. Included in the ducting for double entry compressor engines is the plenum chamber. This chamber is necessary for a double entry compressor, because the air must enter the engine at almost right angles to the engine axis. Therefore, in order to give a positive flow, the air must surround the engine compressor at a positive pressure before entering the compressor. Included in some installations as necessary parts of the plenum chamber are the auxiliary air intake doors, blow-in doors. These blow-in doors admit air to the engine compartment during ground operation, when air requirements for the engine are in excess of the airflow through the inlet ducts. The doors are held closed by spring action when the engine is not operating. During operation, however, the doors open automatically whenever engine compartment pressure drops below atmospheric pressure. During takeoff and flight, ram air pressure in the engine compartment aids the springs in holding the doors closed. The diffuser is an annular chamber provided with a number of vanes forming a series of divergent passages into the manifold. The diffuser vanes direct the flow of air from the impeller to the manifold at an angle designed to retain the maximum amount of energy imparted by the impeller. They also deliver the air to the manifold at a velocity and pressure satisfactory for use in the combustion chambers. Refer to figure 1-46A. And note the arrow indicating the path of airflow through the diffuser, then through the manifold. The compressor manifold shown in figure 1-46A diverts the flow of air from the diffuser, which is an integral part of the manifold, into the combustion chambers. The manifold has one outlet port for each chamber so that the air is evenly divided. A compressor outlet elbow is bolted to each of the outlet ports. These air outlets are constructed in the form of ducts and are known by a variety of names, such as air outlet ducts, outlet elbows, or combustion chamber inlet ducts. Regardless of the terminology used, these outlet ducts perform a very important part of the diffusion process. That is, they change the radial direction of the airflow to an axial direction, in which the diffusion process is completed after the turn. To help the elbows perform this function in an efficient manner, turning vanes, cascade vanes, are sometimes fitted inside the elbows. These vanes reduce air pressure losses by presenting a smooth, turning surface. Figure 1-46B, Axial Flow Compressor. The axial flow compressor has two main elements, a rotor and a stator. The rotor has blades fixed on a spindle. These blades impel air rearward in the same manner as a propeller because of their angle and airfoil contour. The rotor, turning at high speed, takes in air at the compressor inlet and impels it through a series of stages. From inlet to exit, the air flows along an axial path and is compressed at a ratio of approximately 1.25:1 per stage. The action of the rotor increases the compression of the air at each stage and accelerates it rearward through several stages. With this increased velocity, energy is transferred from the compressor to the air in the form of velocity energy. The stator blades act as diffusers at each stage, partially converting high velocity to pressure. Each consecutive pair of rotor and stator blades constitutes a pressure stage. The number of rows of blades, stages, is determined by the amount of air and total pressure rise required. Compressor pressure ratio increases with the number of compression stages. Most engines utilize up to 16 stages and more. The stator has rows of vanes, which are in turn attached inside an enclosing case. The stator vanes, which are stationary, project radially toward the rotor axis and fit closely on either side of each stage of the rotor blades. In some cases, the compressor case, into which the stator vanes are fitted, is horizontally divided into halves. Either the upper or lower half may be removed for inspection or maintenance of rotor and stator blades. The function of the stator vanes is to receive air from the air inlet duct or from each preceding stage and increase the pressure of the air and deliver it to the next stage at the correct velocity and pressure. They also control the direction of air to each rotor stage to obtain the maximum possible compressor blade efficiency. Shown in figure 1-48 are the rotor and stator elements of a typical axial flow compressor. The first stage rotor blades can be preceded by an inlet guide vane assembly that can be fixed or variable. The guide vanes direct the airflow into the first stage rotor blades at the proper angle and impart a swirling motion to the air entering the compressor. This press swirl, in the direction of engine rotation, improves the aerodynamic characteristics of the compressor by reducing drag on the first stage rotor blades. The inlet guide vanes are curved steel vanes usually welded to steel inner and outer shrouds. At the discharge end of the compressor, the stator vanes are constructed to straighten the airflow to eliminate turbulence. These vanes are called straightening vanes or the outlet vane assembly. The casings of axial flow compressors not only support the stator vanes and provide the outer wall of the axial path the air follows, but they also provide the means for extracting compressor air for various purposes. The stator vanes are usually made of steel with corrosion and erosion-resistant qualities. Quite frequently, they are shrouded, enclosed by a band of suitable material. To simplify the fastening problem, the vanes are welded into the shrouds, and the outer shroud is secured to the compressor housing inner wall by radial retaining screws. 1-41. Front compressor stator casing. Rear compressor stator casing. Compressor rotor compressor rear frame. Rear compressor stator casing. Front compressor stator casing. Figure 1-48. Rotor and stator elements of a typical axial flow compressor. The rotor blades are usually made of stainless steel, with the latter stages being made of titanium. The design of blade attachment to the rotor disc rims varies, but they are commonly fitted into discs by either bulb type or fir tree methods. Figure 1-49. The blades are then locked into place by differing methods. Compressor blade tips are reduced in thickness by cutouts, referred to as blade profiles. These profiles prevent serious damage to the blade or housing should the blades contact the compressor housing. This condition can occur if rotor blades become excessively loose, or if rotor support is reduced by a malfunctioning bearing. Even though blade profiles greatly reduce such possibilities, occasionally a blade may break under stress of rubbing and cause considerable damage to compressor blades and stator vane assemblies. The blades vary in length from entry to discharge because the annular working space, drum to casing, is reduced progressively toward the rear by the decrease in the casing diameter. Figure 1-50. This feature provides for a fairly constant velocity through the compressor, which helps to keep the flow of air constant. The rotor features either drum type or disc type construction. The drum type rotor consists of rings that are flanked to fit one against the other, wherein the entire assembly can then be held together by through bolts. This type of construction is satisfactory for low-speed compressors where centrifugal stresses are low. The disc-type rotor consists of a series of discs machined from aluminum forgings, shrunk over a steel shaft, with rotor blades dovetailed into the disc rims. Another method of rotor construction is to machine the discs and shaft from a single aluminum forging, and then to bolt steel stub shafts on the front and rear of the assembly to provide bulb root fir tree root. Figure 1-49. Common designs of compressor blade attachment to the rotor disc. 1-42. Airflow. Figure 1-50. Drum type compressor rotor. Bearing support surfaces and splins for joining the turbine shaft. The drum type and disc type rotors are illustrated in figures 1-50 and 1-51, respectively. The combination of the compressor stages and turbine stages on a common shaft is an engine referred to as an engine spool. The common shaft is provided by joining the turbine and compressor shafts by a suitable method. The engine spool is supported by bearings, which are seated in suitable bearing housings. Rotor blade, stator blade. As mentioned earlier, there are two configurations of the axial compressor currently in use: the single rotor/spool and the dual rotor/spool, sometimes referred to as solid spool and split spool, two-spool, dual spool. One version of the solid spool, one-spool, compressor uses variable inlet guide vanes. Also, the first few rows of stator vanes are variable. The main difference between variable inlet guide vane, VIGV, and a variable stator vane, VSV, is their position with regard to the rotor blades. VIGV are in front of the rotor blades, and VSV are behind the rotor blades. The angles of the inlet guide vanes and the first several stages of the stator vanes can be variable. During operation, air enters the front of the engine and is directed into the compressor at the proper angle by the variable inlet guide and directed by the VSV. The air is compressed and forced into the combustion section. A fuel nozzle that extends into each combustion liner atomizes the fuel for combustion. These variables are controlled in direct relation to the amount of power the engine is required to produce by the power lever position. Most turbofan engines are of the split spool compressor type. Most large turbofan engines use a large fan with a few stages of compression called the low-pressure spool. These turbofans incorporate two compressors with their respective turbines and interconnecting shafts, which form two physically independent rotor systems. Many dual rotor systems have rotors turning in opposite directions and with no mechanical connection to each other. The second spool, referred to as the high-pressure spool, and is the compressor for the gas generator and core of the engine, supplies air to the combustion section of the engine. The advantages and disadvantages of both types of compressors are included in the following list. Even though each type has advantages and disadvantages, each has its use by type and size of engine. The centrifugal flow compressor's advantages are high pressure rise per stage, efficiency over wide rotational speed range, simplicity of manufacture, and low cost, low weight, and low starting power requirements. The centrifugal flow compressor's disadvantages are its large frontal area for a given airflow and losses in turns between stages. Figure 1-51. Disc-type compressor rotor. 1-43. The axial flow compressor's advantages are high peak efficiencies, small frontal area for given airflow, straight-through flow, allowing high ram efficiency, and increased pressure rise by increasing number of stages, with negligible losses. The axial flow compressor's disadvantages are good efficiencies over only narrow rotational speed range, difficulty of manufacture, and high cost, relatively high weight, and high starting power requirements, partially overcome by split compressors. Diffuser. The diffuser is the divergent section of the engine after the compressor and before the combustion section. It has the all-important function of reducing high-velocity compressor discharge air to increased pressure at a slower velocity. This prepares the air for entry into the flame-burning area of the combustion section at a lower velocity, so that the flame of combustion can burn continuously. If the air passed through the flame area at a high velocity, it could extinguish the flame. Combustion section. The combustion section houses the combustion process, which raises the temperature of the air passing through the engine. This process releases energy contained in the air/fuel mixture. The major part of this energy is required at the turbine or turbine stages to drive the compressor. About squared/cubed of the energy is used to drive the gas generator compressor. The remaining energy passes through the remaining turbine stages that absorb more of the energy to drive the fan, output shaft, or propeller. Only the pure turbojet allows the air to create all the thrust or propulsion by exiting the rear of the engine in the form of a high-velocity jet. These other engine types have some jet velocity out the rear of the engine, but most of the thrust or power is generated by the additional turbine stages driving a large fan, propeller, or helicopter rotor blades. The primary function of the combustion section is, of course, to burn the fuel/air mixture, thereby adding heat energy to the air. To do this efficiently, the combustion chamber must provide the means for proper mixing of the fuel and air to assure good combustion. Burn this mixture efficiently. Cool the hot combustion products to a temperature that the turbine inlet guide vanes/blades can withstand under operating conditions. And deliver the hot gases to the turbine section. The location of the combustion section is directly between the compressor and the turbine sections. The combustion chambers are always arranged coaxially with the compressor and turbine regardless of type, since the chambers must be in a through-flow position to function efficiently. All combustion chambers contain the same basic elements. 1. Casing. 2. Perforated inner liner. 3. Fuel injection system. 4. Some means for initial ignition. 5. Fuel drainage system to drain off unburned fuel after engine shutdown. There are currently 3 basic types of combustion chambers, variations within type being in detail only. These types are 1. Can type. 2. Can annular type. 3. Annular type. The can type combustion chamber is typical of the type used on turboshaft and APUs. Figure 1-52. Each of the Figure 1-52. Can type combustion chamber. 1-44. Can type combustion chambers consists of an outer case or housing, within which there is a perforated stainless steel, highly heat-resistant combustion chamber liner or inner liner. Figure 1-53. The outer case is removed to facilitate liner replacement. Older engines with several combustion cans had each can with interconnector, flame propagation tube, which was a necessary part of the can-type combustion chambers. Since each can is a separate burner operating independently of the other cans, there must be some way to spread combustion during the initial starting operation. This is accomplished by interconnecting all the chambers. As the flame is started by the spark igniter plugs in 2 of the lower chambers, it passes through the tubes and ignites the combustible mixture in the adjacent chamber. and continues until all the chambers are burning. The flame tubes vary in construction details from one engine to another, although the basic components are almost identical. Figure 1-54. The spark igniters previously mentioned are normally 2 in number, and are located in 2 of the can-type combustion chambers. Another very important requirement in the construction of combustion chambers is providing the means for draining unburned fuel. This drainage prevents gunk deposits in the fuel manifold, nozzles, and combustion chambers. These deposits are caused by the residue left when the fuel evaporates. Probably most important is the danger of afterfire, if the fuel is allowed to accumulate after shutdown. If the fuel is not drained, a great possibility exists that, at the next starting attempt, the excess fuel in the combustion chamber will ignite, and exhaust gas temperature will exceed safe operating limits. Figure 1-53. Inside view of a combustion chamber liner. The liners of the can-type combustors have perforations of various sizes and shapes, each hole having a specific purpose and effect on flame propagation within the liner. Figure 1-52. The air entering the combustion chamber is divided by the proper holes, louvers, and slots into 2 main streams, primary and secondary air. The primary or combustion air is directed inside the liner at the front end, where it mixes with the fuel and is burned. Secondary or cooling air passes between the outer casing and the liner, and joins the combustion gases through larger holes toward the rear of the liner, cooling the combustion gases from about 3,500 degrees Fahrenheit to near 1,500 degrees Fahrenheit. To aid in atomization of the fuel, holes are provided around the fuel nozzle in the dome or inlet end of the can-type combustor liner. Louvers are also provided along the axial length of the liners to direct a cooling. Interconnector tube. Interconnector tube elbow seal through seal elbow extension tube. Figure 1-54. Interconnecting flame tubes for can-type combustion chambers. 1-45. Layer of air along the inside wall of the liner. This layer of air also tends to control the flame pattern by keeping it centered in the liner, thereby preventing burning of the liner walls. Figure 1-55 illustrates the annular combustion chamber liner. Some provision is always made in the combustion chamber case for installation of a fuel nozzle. The fuel nozzle delivers the fuel into the liner in a finely atomized spray. The more the spray is atomized, the more rapid and efficient the burning process is. 2 types of fuel nozzle currently being used in the various types of combustion chambers are the simplex nozzle and the duplex nozzle. The construction features of these nozzles are covered in greater detail in Chapter 2, Engine Fuel and Fuel Metering Systems. The spark igniter plugs of the annular combustion chamber are the same basic type used in the can-type combustion chambers, although construction details may vary. There are usually 2 igniters mounted on the bus provided on each of the chamber housings. The igniters must be long enough to protrude from the housing into the combustion chamber. The burners are interconnected by projecting flame tubes, which facilitate the engine starting process as mentioned previously in the can-type combustion chamber familiarization. The flame tubes function identically to those previously discussed, differing only in construction details. The can-annular combustion chamber is not used in modern engines. The forward face of each chamber presents 6 apertures, which align with the 6 fuel nozzles of the corresponding fuel nozzle cluster. Figure 1-56. These nozzles are the dual orifice, duplex, type requiring the use of a flow divider. Pressurizing valve. As mentioned in the can-type combustion chamber discussion, around each nozzle are press swirl vanes for imparting a swirling motion to the fuel spray, which results in better atomization of the fuel, better burning, and efficiency. The swirl vanes function to provide 2 effects imperative to proper flame propagation. 1. High flame speed, better mixing of air and fuel, ensuring spontaneous burning. 2. Low air velocity axially, swirling eliminates overly rapid flame movement axially. The swirl vanes greatly aid flame propagation, since a high degree of turbulence in the early combustion and cooling stages is desirable. The vigorous mechanical mixing of the fuel vapor with the primary air is necessary, since mixing by diffusion alone is too slow. This same mechanical mixing is also established by other means, such as placing coarse screens in the diffuser outlet, as is the case in most agile flow engines. The can-annular combustion chambers also must have the required fuel drain valves located in 2 or more of the bottom chambers, assuring proper drainage and elimination of residual fuel burning at the next start. The flow of air through the holes and louvers of the can-annular chambers is almost identical with the flow through other types of burners. Figure 1-56. Special baffling is used to swirl the combustion airflow and to give it turbulence. Figure 1-57 shows the flow of combustion air, metal cooling air, and the diluent or gas cooling air. The airflow direction is indicated by the arrows. Outlet ducts. Flame tubes. Rotor shaft. Fuel nozzle cluster spark igniter. Figure 1-56. Canannular combustion chamber components and arrangement. Figure 1-55. Annular combustion chamber liner. 1-46. Combustion air metal cooling air gas cooling air. Figure 1-57. Airflow through a canannular combustion chamber. The basic components of an annular combustion chamber are a housing and a liner, as in the can type. The liner consists of an undivided circular shroud extending all the way around the outside of the turbine shaft housing. The chamber is constructed of heat-resistant materials, which are sometimes coated with thermal barrier materials, such as ceramic materials. The annular combustion chamber is illustrated in Figure 1-58. Modern turbine engines usually have an annular combustion chamber. As can be seen in Figure 1-59, the annular combustion chamber also uses louvers and holes to prevent the flame from contacting the side of the combustion chamber. Turbine Section. The turbine transforms a portion of the kinetic velocity energy of the exhaust gases into mechanical energy to drive the gas generator compressor and accessories. The sole purpose of the gas generator turbine is to absorb approximately 60 to 70% of the total pressure energy from the exhaust gases. The exact amount of energy absorption at the turbine is determined by the load the turbine is driving, that is, compressor size and type, number of accessories, and the load applied by the other turbine stages. These turbine stages can be used to drive a low-pressure compressor, fan, propeller, and shaft. The turbine section of a gas turbine engine is located aft, or Figure 1-59. Combustion chamber louvers and holes. Downstream of the combustion chamber. Specifically, it is directly behind the combustion chamber outlet. The turbine assembly consists of two basic elements: turbine inlet guide vanes and turbine disc. Figures 1-60 and 1-61. The stator element is known by a variety of names, of which turbine inlet nozzle vanes, turbine inlet guide vanes, and nozzle diaphragm are three of the most commonly used. The turbine inlet nozzle vanes are located directly aft of the combustion chambers and immediately forward of the turbine wheel. This is the highest or hottest temperature that comes in contact with metal components in the engine. The turbine inlet temperature must be controlled, or damage will occur to the turbine inlet vanes. After the combustion chamber has introduced the heat energy into the mass airflow and delivered it evenly to the turbine inlet nozzles, the nozzles must prepare the mass airflow to drive the turbine rotor. The stationary vanes of the turbine inlet nozzles are contoured and set at such an angle that they form a number of small nozzles discharging gas at extremely high speed. Thus, the nozzle converts a varying portion of the heat and pressure energy to velocity energy that can then be converted to mechanical energy through the turbine blades. Figure 1-58. Annular combustion chamber with ceramic coating. Figure 1-60. Turbine inlet guide vanes. 1-47. Figure 1-61. Turbine disc. There are three types of turbine blades: the impulse turbine blade, reaction turbine blade, and the reaction impulse turbine blade. The impulse turbine blade is also referred to as a bucket. This is because as the stream of air strikes the center of the blade, it changes the direction of the energy as it causes the blades to rotate the disc and rotor shaft. The turbine nozzle guide vanes can usually be adjusted during engine overhaul and assembly in order to increase the efficiency of the airstream striking the blades or buckets of the turbine. Figure 1-62. Reaction turbine blades cause the disc to rotate by the aerodynamic action of the airstream directed to flow past the blade at a particular angle in order to develop the most efficient power from the turbine engine. Figure 1-62. The reaction impulse turbine blade combines the action of both the impulse and reaction blades designs. The blade has more of the bucket shape of the impulse blade at the blade root, and it also has more of an airfoil shape of the reaction blade on the second half of the blade toward the outer end of the blade. The second purpose of the turbine inlet nozzle is to deflect the gases to a specific angle in the direction of turbine wheel rotation. Since the gas flow from the nozzle must enter the turbine blade passageway while it is still rotating, it is essential to aim the gas in the general direction of turbine rotation. The turbine inlet nozzle assembly consists of an inner shroud and an outer shroud between which the nozzle vanes are fixed. The number and size of inlet vanes employed vary with different types and sizes of engines. Figure 1-63 illustrates typical turbine inlet nozzles featuring loose and welded vanes. The vanes of the turbine inlet nozzle may be assembled between the outer and inner shrouds or rings in a variety of ways, although the actual elements may vary slightly in configuration and construction features. There is one characteristic peculiar to all turbine inlet nozzles: the nozzle vanes must be constructed to allow thermal expansion. Otherwise, there would be severe distortion or warping of the metal components because of rapid temperature changes. The thermal expansion of turbine nozzles is accomplished by one of several methods. One method necessitates loose assembly of the supporting inner and outer vane shrouds. Figure 1-63A. Each vane fits into a contoured slot in the shrouds, which conforms to the airfoil shape of the vane. These slots are slightly larger than the vanes to give a loose fit. For further support, the inner and outer shrouds are encased by inner and outer support rings, which provide increased strength and rigidity. These support rings also facilitate removal of the nozzle vanes as a unit. Without the rings, the vanes could fall out as the shrouds were removed. Another method of thermal expansion construction is to fit the vanes into inner and outer shrouds. However, in this method the vanes are welded or riveted into position. Figure 1-63B. Some means must be provided to allow thermal expansion. Therefore, either the inner or the outer shroud ring is cut into segments. The saw cuts separating the segments allow sufficient expansion to prevent stress and warping of the vanes. The rotor element of the turbine section consists essentially of a shaft and a wheel. Figure 1-64. The turbine wheel is a dynamically balanced unit consisting of blades attached to a rotating disc. The disc, in turn, is attached to the main power transmitting shaft of the engine. The exhaust gases leaving the turbine inlet nozzle vanes act on the blades of the turbine wheel, causing the assembly to rotate at a very high rate of speed. The high rotational speed imposes severe centrifugal loads on the turbine wheel, and at the same time the elevated temperatures result in a lowering of the strength of the material. Consequently, the engine speed and temperature must be controlled to keep turbine operation within safe limits. The turbine disc is referred to as such without blades. When the turbine blades are installed, the disc then becomes the turbine wheel. The disc acts as an anchoring component for the turbine blades. Since the disc is bolted or welded to the shaft, the blades can transmit to the rotor shaft the energy they extract from the exhaust gases. The disc rim is exposed to the hot gases passing through the blades, and absorbs considerable heat from these gases. In addition, the rim also absorbs heat from the turbine blades by conduction. Hence, disc rim temperatures are normally high, and well above the temperatures of the more remote. 1-48. Rotor. Moving buckets. Steam pressure. Rotor. Stator. Steam velocity. Fixed nozzle. Impulse turbine. Rotor. Stator. Rotor. Steam pressure. Rotating nozzle. Steam velocity. Reaction turbine. Figure 1-62. Impulse and reaction turbine blades. Inner portion of the disc. As a result of these temperature gradients, thermal stresses are added to the rotational stresses. Additionally, turbine blades are generally more susceptible to operating damage than compressor blades due to the exposure of high temperatures. There are various methods to relieve, at least partially, the aforementioned stresses. One such method is to bleed cooling air back onto the face of the disc. Another method of relieving the thermal stresses of the disc is incidental to blade installation. A series of grooves or notches, conforming to the blade root design, are broached in the rim of the disc. These grooves allow attachment of the turbine blades to the disc. At the same time, space is provided by the notches for thermal expansion of the disc. Sufficient clearance exists between the blade root and the 1-49. A. Turbine nozzle vane assembly with loose-fitting vanes. Figure 1-65. Turbine blade with fir tree design and lock tab method of blade retention. B. Turbine nozzle vane assembly with welded vanes. Figure 1-63. Typical turbine nozzle vane assemblies. Notch to permit movement of the turbine blade when the disc is cold. During engine operation, expansion of the disc decreases the clearance. This causes the blade root to fit tightly in the disc rim. The turbine shaft is usually fabricated from alloy steel. Figure 1-64. It must be capable of absorbing the high torque loads that are exerted on it. The methods of connecting the shaft to the turbine disc vary. In one method, the shaft is welded to the disc, which has a Figure 1-64. Rotor elements of the turbine assembly. Butt or protrusion provided for the joint. Another method is by bolting. This method requires that the shaft have a hub that fits a machined surface on the disc face. Then, the bolts are inserted through holes in the shaft hub and anchored in tapped holes in the disc. Of the two connection methods, bolting is more common. The turbine shaft must have some means for attachment to the compressor rotor hub. This is usually accomplished by a spline cut on the forward end of the shaft. The spline fits into a coupling device between the compressor and turbine shafts. If a coupling is not used, the splint end of the turbine shaft may fit into a splint recess in the compressor rotor hub. This splint coupling arrangement is used almost exclusively with centrifugal compressor engines, while axial compressor engines may use either of these described methods. There are various ways of attaching turbine blades, some similar to compressor blade attachment. The most satisfactory method utilizes the fir tree design. Figure 1-65. The blades are retained in their respective grooves by a variety of methods, the more common of which are peening, welding, lock tabs, and riveting. Figure 1-66 shows a typical turbine wheel using rivets for blade retention. The peening method of blade retention is used frequently in various ways. One of the most common applications of peening requires a small notch to be ground in the edge of the blade fir tree root prior to the blade installation. After the blade is inserted into the disc, the notch is filled by the disc metal, which is flowed into it by a small punch mark made in the disc adjacent to the notch. The tool used for this job is similar to a center punch. 1-50. Figure 1-66. Rivet method of turbine blade retention. Another method of blade retention is to construct the root of the blade so that it contains all the elements necessary for its retention. This method uses the blade root as a stop made on one end of the root so that the blade can be inserted and removed in one direction only, while on the opposite end is a tang. This tang is bent to secure the blade in the disc. Turbine blades may be either forged or cast, depending on the composition of the alloys. Most blades are precision cast and finish ground to the desired shape. Many turbine blades are cast as a single crystal, which gives the blades better strength and heat properties. Heat barrier coating, such as ceramic coating, and airflow cooling help keep the turbine blades and inlet nozzles cooler. This allows the exhaust temperature to be raised, increasing the efficiency of the engine. Figure 1-67 shows a turbine blade with air holes for cooling purposes. Most turbines are open at the outer perimeter of the blades. However, a second type called the shrouded turbine is sometimes used. The shrouded turbine blades, in effect, form a band around the outer perimeter of the turbine wheel. This improves efficiency and vibration characteristics and permits lighter stage weights. On the other hand, it limits turbine speed and requires more blades. Figure 1-68. In turbine rotor construction, it occasionally becomes necessary to utilize turbines of more than one stage. A single turbine wheel often cannot absorb enough power from the exhaust gases to drive the components dependent on the turbine for rotative power. Thus, it is necessary to add additional turbine stages. A turbine stage consists of a row of stationary vanes or nozzles, followed by a row of rotating blades. In some models of turboprop engine, as many as 5 turbine stages have been utilized successfully. It should be remembered that, regardless of the number of wheels necessary for driving engine components, there is always a turbine nozzle preceding each wheel. As was brought out in the preceding discussion of turbine stages, the occasional use of more than one turbine wheel is warranted in cases of heavy rotational loads. It should also be pointed out that the same loads that necessitate multi-stage turbines often make it advantageous to incorporate multiple compressor rotors. In the single-stage rotor turbine, the power is developed by one turbine rotor, and all engine-driven parts are driven by this single wheel. Figure 1-69. This arrangement is used on engines where the need for low weight and compactness predominates. This is the simplest version of the pure turbojet engine. A multi-stage turbine is shown in Figure 1-70. In multiple spool engines, each spool has its own set of turbine stages. Each set of turbine stages turns the compressor attached to it. Most turbofan engines have 2 spools, low pressure, fan shaft, a few stages of compression, and the turbine to drive it. Figure 1-67. Turbine blade with cooling holes. Figure 1-68. Shrouded turbine blades. 1-51. Figure 1-69. Single-stage rotor turbine. Figure 1-72. Turbine casing assembly. Figure 1-70. Multirotor turbine. Figure 1-71. Dual rotor turbine for split spool compressor and high pressure. high-pressure compressor shaft, and high-pressure turbine. Figure 1-7. The remaining element to be discussed concerning turbine familiarization is the turbine casing or housing. The turbine casing encloses the turbine wheel and the nozzle vane assembly, and at the same time gives either direct or indirect support to the stator elements of the turbine section. It always has flanges provided front and rear for bolting the assembly to the combustion chamber housing and the exhaust cone assembly, respectively. A turbine casing is illustrated in Figure 1-72. Exhaust section. The exhaust section of the gas turbine engine consists of several components. Although the components have individual purposes, they also have one common function. They must direct the flow of hot gases rearward in such a manner as to prevent turbulence, and, at the same time, impart a high final or exit velocity to the gases. In performing the various functions, each of the components affects the flow of gases in different ways. The exhaust section is located directly behind the turbine section, and ends when the gases are ejected at the rear in the form of a high-velocity exhaust gases. The components of the exhaust section include the exhaust cone, tailpipe, if required, and the exhaust nozzle. The exhaust cone collects the exhaust gases discharged from the turbine section, and gradually converts them into a solid flow of gases. In performing this, the velocity of the gases is decreased slightly, and the pressure increased. This is due to the diverging passage between the outer duct and the inner cone. That is, the annular area between the two units increases rearward. The exhaust cone assembly consists of an outer shell or duct, an inner cone, 3 or 4 radial hollow struts or fins, and the necessary number of tie rods to aid the struts in supporting the inner cone from the outer duct. The outer shell or duct is usually made of stainless steel, and is attached to the rear flange of the turbine case. This element collects the exhaust gases, and delivers them directly to the exhaust nozzle. The duct must be constructed to include such features as a predetermined number of thermocouple bosses for installing exhaust temperature thermocouples. And there must also be insertion holes for the supporting tie rods. In some cases, tie rods are not used for supporting the inner cone. If such is the case, the hollow struts provide the sole support of the inner cone, the struts being spot welded in position to the inside surface of the duct and to the inner cone, respectively. Figure 1-73. The radial struts actually have a twofold function. They not only support the inner cone in the exhaust duct, but they also perform the important function of straightening the swirling exhaust gases that would otherwise leave the turbine at an angle of approximately 45 degrees. The centrally located inner cone fits rather closely against the rear face of the turbine disc, preventing turbulence of the gases as they leave the turbine wheel. The cone is supported by the radial struts. In some configurations, a small hole is located in the exit tip of the cone. This hole allows cooling air to be circulated from the aft end of the cone, where the 1-52 outer duct, insulation blanket, ram air induction air cooling air ejector, inner cone struts. Figure 1-73. Exhaust collector with welded support struts. Pressure of the gases is relatively high into the interior of the cone, and consequently against the face of the turbine wheel. The flow of air is positive, since the air pressure at the turbine wheel is relatively low due to rotation of the wheel. Thus, air circulation is assured. The gases used for cooling the turbine wheel return to the main path of flow by passing through the clearance between the turbine disc and the inner cone. The exhaust cone assembly is the terminating component of the basic engine. The remaining component, the exhaust nozzle, is usually considered an airframe component. The tailpipe is usually constructed so that it is semi-flexible. On some tailpipes, a bellows arrangement is incorporated in its construction, allowing movement in installation, maintenance, and in thermal expansion. This eliminates stress and warping which would otherwise be present. The heat radiation from the exhaust cone and tailpipe could damage the airframe components surrounding these units. For this reason, some means of insulation had to be devised. There are several suitable methods of protecting the fuselage structure. Two of the most common are insulation blankets and shrouds. The insulation blanket, illustrated in figures 1-74 and 1-75, consists of several layers of aluminum foil, each separated by a layer of fiberglass or some other suitable material. Although these blankets protect the fuselage from heat radiation, they are used primarily to reduce heat loss from the exhaust system. The reduction of heat loss improves engine performance. Figure 1-74. Exhaust system insulation blanket. There are two types of exhaust nozzle designs: the converging design for subsonic gas velocities, and the converging-diverging design for supersonic gas velocities. These exhaust nozzle designs are discussed in greater detail in Chapter 3, Induction. and exhaust systems. The exhaust nozzle opening may be of either fixed or variable area. The fixed area type is the simpler of the two exhaust nozzles, since there are no moving parts. The outlet area of the fixed exhaust nozzle is very critical to engine performance. If the nozzle area is too large, thrust is wasted. If the area is too small, the engine could choke or stall. A variable area exhaust nozzle is used when an augmenter or afterburner is used due to the increased mass of flow. When the afterburner is activated, it must increase its open area. When the afterburner is selected, when the afterburner is off, the exhaust nozzle closes to a smaller area of opening. Gas turbine engine bearings and seals. The main bearings have the critical function of supporting the main engine rotor. The number of bearings necessary for proper engine support is, for the most part, determined by the length and weight of the engine rotor. The length and weight are directly affected by the type of compressor used in the engine. Naturally, a two-spool compressor requires more bearing support. The minimum number of bearings required to support one shaft is one deep groove ball bearing, thrust, and radial loads, and one straight roller bearing, radial load only. Sometimes, it is necessary to use more than one roller bearing, if the shaft is subject to vibration, or its length is excessive. The gas turbine rotors are supported by ball and roller bearings, which are anti-friction bearings. Figure 1-76. Many newer engines use hydraulic bearings, in which the outside race is surrounded by a thin film of oil. This reduces vibrations transmitted to the engine. 1-53. Cooling air 120 degrees F. Stainless steel shroud -350 degrees F. Fiberglass, aluminum foil, fiberglass silver foil, jet tailpipe 900 degrees F. Exhaust gas 1000 degrees F. Figure 1-75. Insulation blanket with the temperatures obtained at the various locations shown. In general, anti-friction bearings are preferred largely because they offer little rotational resistance, facilitate precision alignment of rotating elements, are relatively inexpensive, are easily replaced, withstand high momentary overloads, are simple to cool, lubricate, and maintain, accommodate both radial and axial loads, and are relatively resistant to elevated temperatures. The main disadvantages are their vulnerability to foreign matter and tendency to fail without appreciable warning. Usually the ball bearings are positioned on the compressor or turbine shaft, so that they can absorb any axial thrust loads or radial loads. Because the roller bearings present a larger working surface, they are better equipped to support radial loads than thrust loads. Therefore, they are used primarily for this purpose. A typical ball or roller bearing assembly includes a bearing support housing, which must be strongly constructed and supported in order to carry the radial and axial loads of the rapidly rotating rotor. The bearing housing usually contains oil seals to prevent the oil leaking from its normal path of flow. It also delivers the oil to the bearing for its lubrication, usually through spray nozzles. The oil seals may be the labyrinth or thread, helical type. These seals also may be pressurized to minimize oil leaking along the compressor shaft. The labyrinth seal is usually pressurized, but the helical seal depends solely on reverse threading too. 1-54. Ball bearing roller bearing. Preformed sleeve bearing slipper bearing. Figure 1-76. Types of main bearings used for gas turbine rotor support. Stop oil leakage. These two types of seals are very similar, differing only in thread size, and the fact that the labyrinth seal is pressurized. Another type of oil seal used on some of the later engines is the carbon seal. These seals are usually spring-loaded and are similar in material and application to the carbon brushes used in electrical motors. Carbon seals rest against a surface provided to create a sealed bearing cavity or void. Thus, the oil is prevented from leaking out along the shaft into the compressor airflow or the turbine section. Figure 1-77. The ball or roller bearing is fitted into the bearing housing and may have a self-aligning feature. If a bearing is self-aligning, it is usually seated in a spherical ring. This allows the shaft a certain amount of radial movement without transmitting stress to the bearing inner race. The bearing surface is usually provided by a machined journal on the appropriate shaft. The bearing is usually locked in position by a steel snap ring or other suitable locking device. The rotor shaft also provides the matching surface for the oil seals in the bearing housing. These machined surfaces are called lands and fit in rather close to the oil seal. Spacers seal housing. Bearing inner race seals. Figure 1-77. Carbon oil seal. 1-55. Turboprop engines. The turbopropeller Turboprop engine is a combination of a gas turbine engine reduction gearbox, and a propeller. Figure 1-78. Turboprops are basically gas turbine engines that have a compressor, combustion chambers, turbine, and an exhaust nozzle, gas generator, all of which operate in the same manner as any other gas engine. However, the difference is that the turbine in the turboprop engine usually has extra stages to extract energy to drive the propeller, in addition to operating the compressor and accessories. The turboprop turbine transmits increased power forward through a shaft and a gear train to drive the propeller. The increased power is generated by the exhaust gases passing through additional stages of the turbine. Some engines use a multirotor turbine with coaxial shafts for independent driving of the compressor and propeller. Although there are 3 turbines utilized in this illustration, as many as 5 turbine stages have been used for driving the 2 rotor elements, propeller and accessories. The exhaust gases also contribute to engine power output through thrust production, although the amount of energy available for thrust is considerably reduced. 2 basic types of turboprop engine are in use: fixed turbine and free turbine. The fixed turbine has a mechanical connection from the gas generator, gas turbine engine, to the reduction gearbox and propeller. The free turbine has only an air link from gas generator to the power turbines. There is no mechanical link from the propeller to the gas turbine engine, gas generator. There are advantages and disadvantages of each system, with the airframe generally dictating the system used. Since the basic components of normal gas turbine and turboprop engines differ slightly only in design features, it should be fairly simple to apply acquired knowledge of the basic gas turbine to the turboprop. The typical turboprop engine can be broken down into assemblies as follows. 1. The power section assembly contains the usual major components of a gas turbine engine, that is, compressor, combustion chamber, turbine, and exhaust sections. 2. The reduction gear or gearbox assembly contains those sections unique to turboprop configurations. 3. The torque emitter assembly transmits the torque from the engine to the gearbox of the reduction section. 4. The accessory drive housing assembly, mounted on the bottom of the compressor air inlet housing. It includes the necessary gear trains for driving all power section driven accessories at their proper RPM in relation to engine RPM. Turboshaft engines. A gas turbine engine that delivers power through a shaft to operate something other than a propeller is referred to as a turboshaft engine. Figure 1-79. The output shaft may be coupled directly to the engine turbine, or the shaft may be driven by a turbine of its own. Free turbine, located in the exhaust stream. As mentioned with the turboprop. The Figure 1-78. PT6 turboprop engine. 1-56. Figure 1-79. Turboshaft engine. Free turbine rotates independently. This principle is used extensively in current production of turboshaft engines. The turboshaft engine's output is measured in horsepower instead of thrust, because the power output is a turning shaft. Turbofan engines. The turbofan gas turbine engine is, in principle, the same as a turboprop, except that the propeller is replaced by a duct-enclosed axial flow fan. Figure 1-80. The fan can be a part of the first stage compressor blades, or can be mounted as a separate set of fan blades. The blades are mounted forward of the compressor. The general principle of the fan engine is to convert more of the fuel energy into pressure. With more of the energy converted to pressure, a greater product of pressure times area can be achieved. One of the major advantages is turbofan production of this additional thrust without increasing fuel flow. The end result is fuel economy with the consequent increase in range. Because more of the fuel energy is turned into pressure in the turbofan engine, additional stages must be added in the turbine section to provide the power to drive the fan. This means there is less energy left over, and less thrust from the core exhaust gases. Also, in a mixed exhaust nozzle, where fan air and core air mix in a common nozzle before entering ambient conditions, the exhaust nozzle must be larger in area. The result is that the fan develops most of the thrust. The thrust produced by the fan more than makes up for the decrease in thrust of the core gas generator of the engine. Depending on the fan design and bypass ratio, it produces 80% of the turbofan engine's total thrust. 2 different exhaust nozzle designs are used with turbofan engines. The air leaving the fan can be ducted overboard by a separate fan nozzle, figure 1-43, or it can be ducted along the outer case of the basic engine to be discharged through the mixed nozzle, core, and fan exhaust together. The fan air is either mixed with the exhaust gases before it is discharged, mixed or common nozzle, or it passes directly to the atmosphere without prior mixing, separate nozzle. Turbofans are the most widely used gas turbine engine for air transport aircraft. The turbofan is a compromise between the good operating efficiency and high thrust capability of a turboprop. and the high speed, high altitude capability of a turbojet. Turbine engine operating principles. The principle used by a gas turbine engine as it provides force to move an airplane is based on Newton's third law. This law states that for every action there is an equal and opposite reaction. Therefore, if the engine accelerates a mass of air, action, it applies a force on the aircraft, reaction. 1-57. The turbofan generates thrust by giving a relatively slower acceleration to a large quantity of air. The old pure turbojet engine achieves thrust by imparting greater acceleration to a smaller quantity of air. This was its main problem with fuel consumption and noise. The mass of air is accelerated within the engine by the use of a continuous flow cycle. Ambient air enters the inlet diffuser where it is subjected to changes in temperature, pressure, and velocity due to ram effect. The compressor then increases pressure and temperature of the air mechanically. The air continues at constant pressure to the burner section, where its temperature is increased by combustion of fuel. The energy is taken from the hot gas by expanding through a turbine which drives the compressor, and by expanding through an exhaust nozzle designed to discharge the exhaust gas at high velocity to produce thrust. The high-velocity gases from the engine may be considered continuous, imparting this force against the aircraft in which it is installed, thereby producing thrust. The formula for thrust can be derived from Newton's second law, which states that force is proportional to the product of mass and acceleration. This law is expressed in the formula F equals m times a, where F equals force in pounds, m equals mass in pounds per seconds, equals acceleration in feet per seconds. In the above formula, mass is similar to weight, but it is actually a different quantity. Mass refers to the quantity of matter, while weight refers to the pull of gravity on that quantity of matter. At sea level under standard conditions, 1 pound of mass has a weight of 1 pound. To calculate the acceleration of a given mass, the gravitational constant is used as a unit of comparison. The force of gravity is 32.2 feet per second squared, foot/seconds 2. This means that a free-falling 1 pound object accelerates at the rate of 32.2 feet per second each second that gravity acts on it. Since the object mass weighs 1 pound, which is also the actual force imparted to it by gravity, it can be assumed that a force of 1 pound accelerates a 1-1 object at the rate of 32.2 feet/seconds 2. Figure 1-80. Turbofan Engine. 1-58. Or F equals. F equals. F equals. Fn equals. F equals. Also, a force of 10 pound accelerates a mass of 10 pound at the rate of 32.2 feet/seconds 2. This is assuming there is no friction or other resistance to overcome. It is now apparent that the ratio of the force in pounds is to the mass in pounds, as the acceleration in foot/seconds 2 is to 32.2. Using m to represent the mass in pounds, the formula may be expressed thus: F equals m/g, where F equals force, m equals mass, a equals acceleration, g equals gravity. In any formula involving work, the time factor must be considered. It is convenient to have all time factors in equivalent units, that is, seconds, minutes, or hours. In calculating jet thrust, the term pounds of air per second is convenient, since the second is the same unit of time used for the force of gravity. Thrust. Using the formula below, compute the force necessary to accelerate a mass of 50 pounds by 100 feet/seconds 2. MAG. 50 pounds times 100 feet/seconds 2. F equals 32.2 feet/seconds 2. 5,000 pounds foot/seconds 2. F equals 32.2 feet/seconds 2. F equals 155 pounds. This illustrates that if the velocity mass per second is increased by 100, the resulting thrust is 155 pounds. Since the turbojet engine accelerates air, the following formula can be used to determine jet thrust. F equals Miss V2 V1 G, where F equals force in pounds, Miss equals mass flow in pounds/seconds, V1 equals inlet velocity, V2 equals jet velocity, exhaust, V2 minus V1 equals change in velocity, difference between inlet velocity and jet velocity, G equals acceleration of gravity, or 32.2 feet/seconds 2. As an example, to use the formula for changing the velocity of 100 pounds of mass airflow per second from 600 feet/seconds to 800 feet/seconds, the formula can be applied as follows: 100 pounds/seconds, 800 feet/seconds minus 600 feet/seconds, 32.2 feet/seconds 2. 20,000 pounds/seconds, 32.2 feet/seconds 2. F equals 621 pounds. As shown by the formula, if the mass airflow per second and the difference in the velocity of the air from the intake to the exhaust are known. It is easy to compute the force necessary to produce the change in the velocity. Therefore, the thrust of the engine must be equal to the force required to accelerate the air mass through the engine. Then, by using the symbol Fn for thrust pounds, the formula becomes Ms. V2, V1, G. Thrust of a gas turbine engine can be increased by two methods: increasing the mass flow of air through the engine, or increasing the gas velocity. If the velocity of the turbojet engine remains constant with respect to the aircraft, the thrust decreases if the speed of the aircraft is increased. This is because V1 increases in value. This does not present a serious problem. However, because as the aircraft speed increases, more air enters the engine, and jet velocity increases, the resultant net thrust is almost constant with increased airspeed. The Brayton cycle is the name given to the thermodynamic cycle of a gas turbine engine to produce thrust. This is a variable volume constant pressure cycle of events, and is commonly called the constant pressure cycle. A more recent term is continuous combustion cycle. The four continuous and constant events are intake, compression, expansion, includes power, and exhaust. These cycles are discussed as they apply to a gas turbine engine. In the intake cycle, air enters at ambient pressure and a constant volume. It leaves the intake at an increased pressure and a decrease in volume. At the compressor section, air is received from the intake at an increased pressure, slightly above ambient, and a slight decrease in volume. Air enters the compressor where it is compressed. It leaves the compressor with a large increase in 1-59 pressure and decrease in volume, created by the mechanical action of the compressor. The next step, expansion, takes place in the combustion chamber by burning fuel, which expands the air by heating it. The pressure remains relatively constant, but a marked increase in volume takes place. The expanding gases move rearward through the turbine assembly, and are converted from velocity energy to mechanical energy by the turbine. The exhaust section, which is a convergent duct, converts the expanding volume and decreasing pressure of the gases to a final high velocity. The force created inside the engine to keep this cycle continuous has an equal and opposite reaction, thrust, to move the aircraft forward. Bernoulli's principle. Whenever a stream of any fluid has its velocity increased at a given point, the pressure of the stream at that point is less than the rest of the stream, is applied to gas turbine engines through the design of convergent and divergent air ducts. The convergent duct increases velocity and decreases pressure. The divergent duct decreases velocity and increases pressure. The convergent principle is usually used for the exhaust nozzle. The divergent principle is used in the compressor and diffuser where the air is slowing and pressurizing. Gas turbine engine performance. Thermal efficiency is a prime factor in gas turbine performance. It is the ratio of net work produced by the engine to the chemical energy supplied in the form of fuel. The three most important factors affecting the thermal efficiency are turbine inlet temperature, compression ratio, and the component efficiencies of the compressor and turbine. Other factors that affect thermal efficiency are compressor inlet temperature and combustion efficiency. Figure 1-81 shows the effect that changing compression ratio, compressor pressure ratio, has on thermal efficiency when compressor inlet temperature and the component efficiencies of the compressor and turbine remain constant. The effects that compressor and turbine component efficiencies have on thermal efficiency when turbine and compressor inlet temperatures remain constant are shown in Figure 1-82. In actual operation, the turbine engine exhaust temperature varies directly with turbine inlet temperature at a constant compression ratio. RPM is a direct measure of compression ratio. Therefore, at constant RPM, maximum thermal efficiency can be obtained by maintaining the highest possible exhaust temperature. Since engine life is greatly reduced at high turbine inlet temperatures, the operator should not exceed the exhaust temperatures specified for continuous operation. Figure 1-83 illustrates the effect of turbine inlet temperature on turbine blade life. In the previous discussion, it was assumed that the state of the air at the inlet to the compressor remains 30. Thermal efficiency, in percent, efficiency of C&T 90%, 80%, 85%, 75%, 25, 20, 15, 10, 5, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. Compression ratio. Figure 1-82. Turbine and compressor efficiency versus thermal efficiency. Thermal efficiency, in percent, 30, 25, 20, 15, 10, 5. Temperature, 1000 degrees Fahrenheit, 1200 degrees Fahrenheit, 1400 degrees Fahrenheit, 1600 degrees Fahrenheit. Turbine inlet temperature increase. 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. Compression ratio. Figure 1-81. The effect of compression ratio on thermal efficiency. 1-60. 0, 100, 200, 300, 400, 500. Turbine bucket life, in hours. Figure 1-83. Effect of turbine inlet temperature on turbine bucket life. Constant. Since this is a practical application of a turbine engine, it becomes necessary to analyze the effect of varying inlet conditions on the thrust or power produced. The three principal variables that affect inlet conditions are the speed of the aircraft, the altitude of the aircraft, and the ambient temperature. To make the analysis simpler, the combination of these three variables can be represented by a single variable called stagnation density. The power produced by a turbine engine is proportional to the stagnation density at the inlet. The next three illustrations show how changing the density by varying altitude, airspeed, and outside air temperature affects the power level of the engine. Figure 1-84 shows that the thrust output improves rapidly with a reduction in outside air temperature, OAT, at constant altitude, RPM, and airspeed. This increase occurs partly because the energy required per pound of airflow to drive the compressor varies directly with the temperature, leaving more energy to develop thrust. In addition, the thrust output increases since the air at reduced temperature has an increased density. The increase in density causes the mass flow through the engine to increase. The altitude effect on thrust, as shown in Figure 1-85, can also be discussed as a density and temperature effect. In this case, an increase in altitude causes a decrease in pressure and temperature. Since the temperature lapse rate is lower than the pressure lapse rate as altitude is increased, the density is decreased. Although the decreased temperature increases thrust, the effect of decreased density more than offsets the effect of the colder temperature. The net result of increased altitude is a reduction in the thrust output. The effect of airspeed on the thrust of a gas turbine engine is shown in Figure 1-86. To explain the airspeed effect, it, constant altitude, RPM, and airspeed, net thrust, 100%, 60%, Deck STD Inc., outside air temperature, OAT, 100, constant airspeed, and RPM, thrust, percent sea level rated, 50, 0, 0, 10, 20, 30, 40, 50, altitude, 1000 of foot. Figure 1-85. Effect of altitude on thrust output, 100, constant RPM, altitude, and OAT. Net thrust, 50. With ram. Without ram, 0, 0. Increase. Figure 1-86. Effect of airspeed on net thrust. Is necessary to understand first the effect of airspeed on the factors that combine to produce net thrust, specific thrust, and engine airflow. Specific thrust is the net thrust in pounds developed per pound of airflow per second. It is the remainder of specific gross thrust minus specific ram drag. As airspeed is increased, ram drag increases rapidly. The exhaust velocity remains relatively constant. Thus, the effect of the increase in airspeed results in decreased specific thrust. Figure 1-86. In the low speed range, the specific thrust decreases faster than the airflow increases, and causes a decrease in net thrust. As the airspeed increases into the higher range, the airflow increases faster than the specific thrust decreases, and causes the net thrust to increase until sonic velocity is reached. The effect of the combination on net thrust is illustrated in Figure 1-87. Figure 1-84. Effect of OAT on thrust output, 1-61. Ram recovery. A rise in pressure above existing outside atmospheric pressure at the engine inlet, as a result of the forward velocity of an aircraft, is referred to as ram pressure. Since any ram effect causes an increase in compressor entrance pressure over atmospheric, the resulting pressure rise causes an increase in the mass airflow and gas velocity, both of which tend to increase thrust. Although ram effect increases engine thrust, the thrust being produced by the engine decreases for a given throttle setting as the aircraft gains airspeed. Therefore, two opposing trends occur when an aircraft speed is increased. What actually takes place is the net result of these two different effects. An engine's thrust output temporarily decreases as aircraft speed increases from static, but soon ceases to decrease. Moving toward higher speeds, thrust output begins to increase again due to the increased pressure of ram recovery. Constant RPM, altitude, and OAT, airflow, In pounds/seconds, total airflow, W, specific thrust, 0, increase. Figure 1-87. Effective airspeed on specific thrust, and total engine airflow. 1-62. Chapter 2. Engine fuel, and fuel metering systems.